Hello, everyone. Welcome to WQRF's third summer school session of 2025. Join us each month through August, and we look forward to covering hot topics in water all summer long. My name is Lilia, and I'm the project coordinator here at WQRF. I want to give a special thanks to Calgon Carbon Corporation for sponsoring the entire summer school series. We are grateful for their support in making this education free for all stakeholders in water. We will email you a recording of today's webinar, but you can also visit our website at wqrf.org/webinars to see the recordings. Dr. George Zhou and Dr. Angie Rodriguez are our presenters today. George will summarize his ongoing research on PFAS retention in spent filters under simulated landfill conditions. Angie will provide industry insight from Calgon Carbon about reactive processes to remove PFAS. Dr. Zhou is an associate professor at Purdue University. His research centers on environmental engineering, including wastewater treatment, water reuse, and water quality, and environmental biotechnologies. His recent projects have explored water filtration, PFAS, antibiotics, and biofuels. He holds a professional engineer license in California, is a board-certified environmental engineer, and an Envision sustainability professional. Dr. Angela Rodriguez is the technical director of Calgon Carbon's Drinking Water Solutions and Innovative Carbon Technologies business units. She has over 10 years of experience in the water industry and has worked on projects spanning from source water to tap water. She has published 4 peer-reviewed papers and regularly gives presentations at local, regional, and national conferences. Angela's passion lies in operations research and helping utilities find cost-effective solutions to meet today's regulatory landscape. So with that, I will turn it over to George and Angie to begin their presentations.
Hi, good morning and good afternoon, depends on where you're coming from. So I'm really glad to share some of our research results on the retention of PFAS on spent filters. So you probably have already heard this group of chemicals, per and polyfluoroalkyl substances. The short name is PFAS or PFAS. So it includes a group of nearly 15,000 synthetic chemicals. Sometimes we call them as forever chemicals because they are highly persistent in the environment. So they have been used in the consumer products since the 1950s. You may have already heard about this. More than 97% of the Americans' blood contains this group of chemicals. And there are studies to show the potential correlation between the exposure to this group of chemicals and some adverse health impacts, health problems such as testicular and kidney cancers, thyroid disease, and metabolic disorders. One of the main challenges of dealing with group of chemicals is very difficult to treat. So let's look at the why it is ubiquitously detected in all the different environment. So the PFAS have been manufactured in different industry, the manufacturers. We could have the wastewater containing the PFAS may actually affect the rivers, lakes, and all the other surface waters. So some of the materials that are used have been treated in the wastewater treatment plant, but even the treated wastewater may contain PFAS. And the biosolid that have been, which is essentially waste sludge, may contain PFAS. And when we transfer those biosolids to the landfills, in the leachate, PFAS are often detected. And biosolids have been used as fertilizers to increase the nutrient concentrations in agriculture. And we have the infiltration, and that may also transfer some of the PFAS to the groundwater and also surface water. Some of the PFAS compounds are also volatile, so we have this atmospheric deposition of PFAS. In drinking water, PFAS have been also frequently detected, even though their concentrations are relatively low. But whenever we are talking about the drinking water, even gray water, and oftentimes we see this group of compounds. Because of the frequent detection and wide occurrence of PFAS. So PFAS regulations have been developed during the last decades. So back in 2016, we had these lifetime health advisories for two types of PFAS, PFOA and PFOS, for about like 70 ppt, which is parts per trillion. And 6 years later, the Comprehensive Environmental Response Compensation and Liability Act, we call circular, they have identified health advisory levels of PFOA and PFOS of 0.004 and 0.002 ppd respectively. 2 years ago, actually last year, EPA published the final maximum contamination levels, MCLs, for 6 PFAS compounds, PFOA, PFOS, PFHXS, PFNA, PFBS, and GenX in this National Primary Drinking Water Regulations. Just back in May, so EPA published another news to show, okay, they may change some of the rules to regulate only the PFOA and the PFOS. But still, regarding the development of the regulation, the PFAS are widely detected. The main challenge for this group of compounds for this kind of regulations and also the potential health risk correlation is that PFAS are really difficult to treat because the carbon fluorine bond within the PFAS is considered the strongest single covalent bonds in organic chemistry, and I have shown the pictures of the typical compounds within the PFAS, most widely studied compound, PFOA and PFOS in the left side. You can see we have multiple CF bonds in these two chemicals. If you look at the right side of the figure, CF bond is in the top right corner, so which means it's much, much stronger compared to other typical carbon-hydrogen bond, which is the foundation for organic chemistry. So you need to have 70% more energy to break the carbon fluorine bond, which means the typical or conventional treatment technologies are usually not very effective to treat this group of chemicals. We have thermal treatment, but usually that needs about like 1,000 degrees. Even the low temperature treatment still requires 200 to 300 Celsius degrees conditions to break down, to destruct these compounds. And some other adsorption filtration technologies have been developed. Today, I would like to focus more on one of the approaches that have been developed, that has been working very effectively to deal with the potential health risks of PFAS. It's point-of-use water filtration systems. So they can remove contaminants at a relatively affordable cost. So the POU systems treat the drinking water right before consumption, regardless of the compounds are regulated or not. And they are relatively affordable, depends on what kind of systems we could purchase. So there are multiple benefits. For example, they are used on as needed basis. You don't have to treat a large amount of the water and store the water because you still need to consider, the microbial growth or other just the large footprint to hold that kind of water. So you just use it when it's needed. And for rural areas, resource-limited regions, or regions with less developed infrastructure, this is a very good option. And POU systems have very good removal efficiencies for both unregulated and regulated contaminants, including emerging contaminants. We have thousands of different unregulated emerging contaminants, and POU systems have been working very well to treat them. So overall, these POU systems are very cost-effective solutions to protect human health. And let's look at, okay. I'm clicking this. Okay, right. So let me share some of these most commonly used POU technologies. One is RO, the other one is AC. The RO is reverse osmosis. It's a pressure-driven membrane filtration technology. you have one influent, you have two effluent. The pressure can come from the pressure in the drinking water distribution systems, usually between 40 to 6 psi. You don't have to put additional pump to provide the pressure. So you can see the picture in the right side. You have 3-stage or 5-stage RO system with the pressure coming from with the tap water. You can just install this. You can have a storage tank and hold the water and drink it whenever it's needed. The picture in the bottom right is a picture of the example of this AC system. So it's activated carbon system. It's an adsorption-based technology. It's called dead end filtration because you have 100% of the water coming in, you have 100% of water going out of the system. That is, in terms of cost, it's even cheaper. But for PFAS removal, both systems are very effective. So overall, we are talking about over 99% removal efficiencies. So these are the POU systems we have been evaluating. One of the things probably a lot of people have not been discussing is that these systems are so effective and working so well, but what's going to happen after they are used? We will not store these filters at home, right? Because it's essentially it's a solid waste. So we actually move them to a landfill. We call them spent filter or used filters. So there's disposed in the landfill, and there's actually a question to ask. So what can happen for PFAS within these kind of filters? So in this study, we actually looked into the fate and transport of the PFAS in spent filters. So we would like to measure the PFAS retention in spent filters, both AC and RO. And we also evaluated the different impact of the environmental factors, including the pH and ionic strength, to see how they may affect the transfer of the PFAS, if PFAS will stay within the spent filters. So let me show you the setup of the RO system. So we have the water, the tap water. Then we have a large feed tank to mix the PFAS compound, 1 microgram per liter, with a mixture of the 6 PFAS compound that have been regulated so far. Then we have a booster pump to pump the water through 3 RO membrane filters. Then these are 3 triplicates, 3 replicates, basically a triplicate. We essentially have the same kind of setup. Then we calculate the amount of PFAS that's being retaining on the filter. So we calculate the average values. We also calculate standard error and standard deviation. So we're going to have a statistically solid results. For the RO membrane, we essentially open up the filter after the use and cut them in small pieces. 1 centimeter to 1 centimeter pieces. So we put, I think, 20 of those in the small polypropylene bottles and run the retention experiments. So we also have another setup for the active carbon systems. We have the same kind of large feed tank. It's about 2,000 liters. Then we also have a booster pump to have 3 replicates, so the triplicate measurements of the AC carbon filters. So the one additional processing procedure here is that the large AC carbon block filter it's too big for the retention experiments, and also because we are measuring the retention for multiple times under multiple conditions, we cannot just have like hundreds of those kind of filters for this comparison studies. So we use blenders to break the AC carbon block filters into small powders, and we have sieves to make sure the particle sizes are homogeneous as much as possible. Then we do the adsorption and desorption experiments to evaluate the retention of the PFAS. So we use a ratio of 1 to 20 between the solid and the liquid to follow the EPA standard. We initially followed the EPA SW846 testing method 1311, which is a toxicity characteristics leaching procedure we call T-clip. But we did modify the procedure a little bit. So instead of using 2 pH, which is 2.88 and 4.93, depending on the initial pH of the material, right? If it's acidic or not, you have to make the change the pH within this retention procedure. So we used a wide range of pH, starting from 2 to 13, to see how the PFAS retention may be affected under this wide range of pH conditions. The typical pH of the landfill leachate is between 6 to 10. Sometimes, the fresh leachate could be a little bit acidic. So we would like to see actually what's going to happen. So we actually run additional testing just with more pH. And in the T-clip, they usually recommended 18 hours test to see how much chemicals are separating or dissolving from the material. But instead of 18 hours, we actually, in addition to the 18 hours, we performed the test, including 18 hours, but also up to 30 days to see the long-term retention potential of the PFAS within the filters. In the T-clip procedure, they use a rotary shaker at 30 RPM. We consider that option, but because of large number of samples, we use an orbital shaker with a higher speed to increase the mixing and mass transfer efficiency. So these are the differences of the tests. So we started from testing the PFAS concentration of the new high-density polyethylene bottles. The bottles have been used for sample collection. We have actually observed the trace amount of PFAS in the new unused bottles, which again shows that the PFAS are ubiquitous. They are detected everywhere. Even for the new sampling bottles, we see very trace amount of the PFAS within the concentration of 9 grams per liter. This is important because we can run the control experiment to subtract this concentration. But because we find this trace amount concentration, we actually use methanol, which is a very good solvent, to rinse those bottles to remove even the trace amount of bioground to make sure the results we are seeing is accurate. The results can reflect the real potential of the PFAS partitioning within the filter and the leachate. So we continue the experiment, and let me click this. Okay, so this is a general diagram to describe the procedure for evaluating the new and non-flushed filters. So we also cut the our membranes and studied the spacers and membrane materials. Then we use solid phase extraction and LCMS to analyze the amount of PFAS within the material by themselves. I'm not showing the data here, but again, this kind of preliminary experiments indicated that even the materials we often use for the filter may also have some PFAS inside. It's really interesting that if we follow the recommended procedure to flush these kind of filters before the use, you are really not able to detect any significant amount of PFAS, which means actually you have to follow the manufacturer's recommendation to properly prime or flush the filter before you actually drink the water produced from the POU systems. Now let's get back to the actual results on the retention experiments. This is a little bit slow. Sorry, I'm clicking, but it's not moving. Okay, so our results indicated that most PFAS were retained in the spent filters. So this is our initial rounds of studies, experiments to show the concentrations within the 30 days. So in the left side, you can see the new filters. So even the new filters may kind of release a small amount of PFAS here, but the concentration is 9 grams per liter is very low. In the right side, you can see, okay, within 30 days, initially you have maybe some of the PFAS detected in the liquid phase, and you have actually variations, especially for the PFBS, but that actually the PFBS concentration also changed back to the low level. So initially we thought, okay, so what's going on within the 21 days? Then we continue the experiment to see what kind of the factors that could have contributed to the high variability. Then we look at the additional, sorry, when I have to click like 3 times. We actually observed high variability when we actually evaluated the retention of the PFAS over a long time under different pH values. So this is a figure to show after 15 days of experiments. And we have seen the cumulative PFAS distributed with a very kind of strange shape. So it looks like pH 4 may be the condition to somehow promote the partitioning from the PFAS into the liquid phase, so the PFAS are less retained. But if you look at the pH 8 and 10, so you see the 2 additional peaks, that doesn't really make much sense. Then we actually check the data and procedure again and again until we realized, okay, one of the options is likely because the preparation procedure of our materials. In this case, for the active carbon, we actually modified the particle because you probably remember we use a blender to break the carbon block filters within small particles. But there are 2 factors here that could affect the evaluation accurately about the PFAS amount retained in the filter. First, the PFAS may be retained or accumulated more on the surface of carbon block filters, and the less PFAS may show up in the internal core of the carbon block filters. So that's one possibility. The second possibility is when you actually break them into small particles, even though we make sure they are having similar physical sizes, you can now use your eyes to homogenize all the small particles because they all look like small, fine black powders. So I think those are the 2 main factors. So to deal with that kind of high variability and reduce the variability caused from this preparation, we changed our particle to ground the active carbon block filters into powders first to try to improve the homogeneity, and we soak them, run the absorption experiments, then just try to see first if we can absorb the similar amount of the PFAS. In this absorption experiment as a filtration experiment, we run this methanol extraction experiment, which is most commonly used solvent to extract the PFAS. Then we run the LCMS and confirm the PFAS are actually absorbed similarly within these carbon block filters. So by changing the procedure to have absorption of all the particles first, then homogenize everything and separate them into different bottles, we are able to come up with a system with much evenly distributed active carbon powder for retention experiments. Then we used the mesh screen to make sure also we have similar uniform particle size. Then we run the retention experiment again. So this time we actually got much less variability and much highly consistent results. So the results show that actually most PFAS were retained on spent filters over time. So these are the results for the initial 12 days, as you can tell. So we have little changes over their concentration during this 12-day incubation or desorption experiments. And most of the concentrations are really, really low. So the total amount is only within the range of like 30 nanogram or 20 nanogram, except the PFBS, which is the only compound that shows a little bit higher concentration compared to other PFAS compound. So this figure shows you the accumulative mass of PFAS. So less PFAS were retained under the conditions with pH above 12. As you can see, you have the bar chart in the right side. When pH is 12 or 13, you have higher concentrations in the water. But for majority of these pH conditions, including those pH, the common pH 6 to 10 for leachate, you have relatively low amount of PFAS. So we zoomed into the data and compare the 6 different PFAS compounds we detected. The PFBS was less retained on spent filters. It's the majority of this, it's like from 88% to 90%. Among all these compounds, they are actually PFBS. So we compare the detailed data. It's really interesting, actually, although the PFAS was retained, was less retained than other PFAS, but over 99.9% of the PFAS was still retained on spent filters. So I use 99.5. Those are the average concentration when PFAS was above 11, which is highly unlikely for landfill leachate. So if you look at all the figures, over the days, within these 12 days, you can see the increased mass of the PFAS. So you see, some of the PFAS are less retained in these filters. If you check the numbers, I know it's kind of hard to see. The bottom right one, under pH 13. So that is the data to show actually under a highly basic pH condition, pH 13, you can have, relatively higher amount of PFAS, which is basically the PFBS. So they dominate the PFAS within the water, and it's much higher than others. But still, it's very small fraction as compared to the PFAS retained in the spent filters. The other thing we look into is to see to try to explain the results with the information about the differences in their structures. So we plotted the amiso PFAS over their chain lengths. So the long chain PFAS were retained strongly than the short chain PFAS. So the PFBS has 4 carbons in their backbone, and PFOA, PFOS have 8, and like PFNA, they have 9 carbon in their backbone. So whenever you see the PFAS compound with shorter chain lengths, so you can see we have higher amount of PFAS within the water, so less amount will be retained. And the trends look similar within the first 18 hours and also for the 12 days. So it doesn't matter if it's short term or long term, even up to 30 days. We have the results. It's now shown here. We see the overall trend is the shorter chain you have, the less likely they will be retained, even though it's like only less than 1%. But if you have higher chain PFAS compound, which is if the main concern, for example, PFOA, PFOS, they have 8 carbons, they are regulated, and you probably don't need to worry too much about it because they are less likely to migrate outside of the spent filters. They'll be strongly retained in the filter. Even after use, you dispose them into the landfill, and you'll very unlikely detect the higher amount of PFAS from this filter, just very lower concentration, because we have the data to show in majority of these retention experiment, the actual number is sometimes, most of the time is 99.99% retention for the long chain PFAS compounds. In addition to pH, we also look at the ionic strength because there could be potential competitions and that may affect the retention of the PFAS. Overall, you have already seen the results in the top left corner, like if you have the higher pH, you have more PFAS migrating to the water. So, but in the bottom left, you can actually see the correlation between the pH and the conductivity. In the bottom right, actually look at that figure. You have the correlation between the conductivity, which is a parameter we use to describe ionic strength, and versus the mass of the PFAS. We have pretty good correlation coefficient. So the R square is more than 90%, which means they are kind of correlated. The results suggest that the ionic strength actually likely going to affect the retention of PFAS. However, when we compare the correlation between pH, conductivity, and amount of PFAS we detected, we run multiple correlation analysis, like in the top right corner of the figure. So it looks like PFAS has much stronger impact as compared to conductivity to affect the behavior, the fate and transport of the PFAS in the spun filters. We are still working on this and have additional data to see the long-term performance. And we are also looking at the impact of pH for the resin. So they are not shown today, but we are about to finish the study really soon. So overall, the main conclusion about this study so far is that PFAS are ubiquitous and can be detected in new sampling bottles, new filters, and it is very important to flush the filter with the recommendation from the POU system manufacturers. So if you have been recommended to use the storage tank twice to flush it for the RO filter, just please do that, because to minimize the background contaminants within the drinking water, even though they will likely not migrate across the membrane, you just still want to follow what's recommended. For AC filter, same thing, flush it, make sure you have, and even some of the particles may somehow accumulated within the new filter, just flush them out to kind of make sure the background compound will not be there. We have seen high variability in the PFAS retention, and that could be related because of heterogeneity resulted from the absorption and grinding process. And because of that potential concern, we have revised the protocol to basically try to find the mechanistic explanation about the fate and transport of PFAS within the spun filters. And we found that the strong retention of the PFAS was observed especially with long-chain PFAS compounds. And also whenever the pH was less than 12, pH greater than 12, let's say pH 13, may reduce the retention a little bit, but not so much. And PFAS retention was affected by both pH and ionic strength, which are the factors that could change quite a bit within the landfill leachate. But looks like pH plays a major role in the retention of the PFAS. And even for the less retained short-chain PFAS, like PFBIs, under very basic conditions, pH greater than 12, a majority, 99.9 actually for most of the data, but if you're only to a very narrow range, 99.5% of the PFAS are still retained on the spun filters. So that's just some of the results we have obtained so far. I'd like to shift to Angie for her presentation. Oh, sorry, by the way, I would like to acknowledge the funding from the WQRF that has been both technical and administrative help and has been greatly helpful for our project. And the co-principal investigators are Professor Linda Lee at Agronomy of Purdue and Dr. Yunjong Choi. She's a senior analytical chemist at Purdue. And also Wanyue Hui is a PhD student at Purdue, and she has been working this just very hard during the last year on getting this kind of high quality data. So I like to shift to Angie for her talk. Yes.
All right. Hello, everyone. Like Lilia said, my name is Angie. I am the technical director here at Calgon Carbon, and today I'm going to talk to you about reactivation and how we've been doing studies to prove that we can actually take that forever chemical and make it not forever anymore. Let me make sure. There we go. So, as you may or may not know, we have various technologies out there that can remove PFAS from our drinking water. The three that are most commonly used are your RO membranes, your ion exchange resins, and your granular activated carbon. Unique to activated carbon, though, is the process of reactivation, where you can use it to dispose of spent material, rather than having it go to an incineration facility or a landfill. Now, when it comes to reactivation, the reason why it is such a benefit to the technology that sometimes is not necessarily quantifiable is one, you are getting rid of that spent material, so there's not necessarily any landfill liabilities. It is generally cheaper than incineration. In addition to that, most incinerators today are having long wait lines for a queue, basically, to get whatever waste you're trying to incinerate rid of, right? So it's definitely a positive for GAC users that they can just go through reactivation as opposed to incineration. But in addition to that, one of the key benefits that is more on like just a wholesome environmental point of view is that it's more sustainable. You are reducing CO2 emissions, you're reusing or finding a reusability to a compound or a material that can be of benefit, and as opposed to always having to mine more and more and more of a limited resource. It is also referenced in the EPA disposal guidance document, as well as it is the DoD's preferred method of disposal for activated carbon. So all in all, it tends to be what our users gravitate towards when it comes to spent material. In terms of just a little bit of background on how reactivation works, it is a four-step, or it's more than that, but to condense it down, it's a four-step temperature process. So the first step is to basically get to a temperature where you're driving off or drying the media that you are reactivating. Once that is done, you're continuing to increase that temperature, and you're going to hit a point where you're going to start to desorb the contaminants that were removed with the GAC while it was online, and those contaminants are then volatilized. Then you're going to increase the temperature once again. And at this time, what's happening is that either some of those compounds that were devolatilized, the temperature in that kiln is either destroying the bonds, the chemical bonds between them, thereby removing the contaminant, but also any inorganics that are left in the media, say calcium, for example, that will end up creating a localized higher temperature in your media, and that's what leads to a little bit of charring, a little bit of mass, quote unquote, loss, which is not you're losing mass, it's just you're basically taking the granule and it's becoming more of a powder. And that's where you get your quote unquote losses through reactivation. And then the final step is again a higher temperature to get to the actual activation or reactivation of that medium. The picture here, just so we're a little clear, is of a multiple hearth furnace. And the way it works is that the carbon, the spent carbon, will come at the top of that structure, and it's going to move down through different, I'm going to call them compartments in that multiple hearth furnace. And as it goes down through those compartments, the temperature is going up. And so you're getting those different layers of temperatures and activities and processes happening. And then at the end is your reactivated product at the bottom. Now, at Calgon, we've been doing reactivation for decades, honestly, but with the onset of PFAS and finding these chemicals and how hard and persistent they are in the environment, we wanted to make sure that our reactivation process was able to actually take that chemical not just off our media, but also actually destroy it and not just put it somewhere else, basically. And so we've conducted multiple studies to verify the actual destruction efficiency of our process for PFAS. And we've detected that it's greater than 99.9 or greater than 99.99 destruction of those compounds. And it's important for this or I guess I should say, it's important for us to prove this because ultimately our customers want that assurance that we're not, taking PFAS out of the water and just putting it somewhere else, like for example, the air. We're actually taking it out of the water and taking it out of the environment through the reactivation process. Now, to calculate that destruction removal efficiency, all you're really doing is a mass balance around your process. So you're looking at your inputs. So that would be your spent carbon, or in other words, the mass of PFAS that's loaded onto that spent carbon. And then you're looking at your outputs. So what's coming out of your kilns in a vapor phase, as well as what's coming out of your stack in a vapor phase. Okay. In terms of how PFAS is measured, there is a EPA method for the actual solids analysis of how much PFAS is in your spent material, and that is what you do to get that input number for your calculations. You're also doing that same method to then measure the reactivated material to make sure that there's no lingering PFAS left on that material. And then when it comes to your air or emissions testing, you are actually using the EPA's OTM 45 method. So it is a vapor phase PFAS method, and it's looking at your polar semi-volatile compounds, and shown in the graph here. So those include 49 different PFAS compounds that are C4 or larger, and in that mixture is your regulated drinking water contaminants such as PFOA and PFOS. Now, so this is a diagram of the process itself, and with the left here showing you that multiple hearth furnace, where the spent carbon is coming in at the top and your reactivated carbon is at the bottom. And the dots here are showing where we sampled through the process. So we collected solid phase extractions for both the spent material, what's coming into our process, as well as the reactivated material, what's coming out. And then we also did vapor phase analysis, what's coming out of our kiln, which is again focused on reactivating the media. And then at the stack, which is downstream of what we call our abatement system or air pollution control system, which is comprised of a thermal oxidizer, which is basically a high temperature or higher temperature furnace that is treating the gases that are coming off of the reactivation kiln. And then once those gases go through that thermal oxidizer, you're going through a chemical scrubber to get rid of any acids that are formed during the process. Then it goes through a bag house to remove any particulates before it goes to that exhaust stack. And this are the results of that study. We found that the spent carbon loading from a total PFAS perspective was around 0.748 pounds per hour. And then we found basically below detection on the reactivated media. So we were able to not just remove the PFAS from the media at these high temperatures, but we're also able to destroy the majority of the PFAS that bond between the carbon fluorine atoms in the kiln itself, showing what we measured at the vapor phase being 8.41 times 10 to the negative 5 pounds per hour of total PFAS going into our abatement system. And then through the abatement system, that gets knocked down further from 8.41 to 4.88 to 10 to the negative 5 pounds per hour. So when you do the actual mass balance calculation, the DRE calculation, you end up with greater than 99.99% destruction of total PFAS through the process, and a reactivated media that does not have PFAS on it and can be reused in other I would say industries such as wastewater or industrial applications. And then just to wrap up with that, I just wanted to add that that study itself has been published. It was published in 2022, and it is open access in the remediation journal, so anybody can go and download that paper and read through it. We have since then completed additional studies, including one that we have basically almost finished writing up, and we should be submitting to the journal very soon, and it should be published Q3 of this year. Again, open access for everybody to download. But it's just another way of us making sure that our processes, our plants are reliable in the destruction of these compounds, and that when you do send us that media, that spent material, you can rest easy that it's not that you're just moving the contaminant elsewhere. We're actually able to remove it from the environment. And then in terms of for this particular audience, we do offer reactivation services for our point of entry style system. So these is not necessarily what Dr. Zhou was looking into, your point of use. So point of entry would be more like a communities system or like your entire house, for example, rather than just say your faucet or like a pitcher of water. That's more point of use. So point of entry is like a bigger system, but usually much smaller than your utilities that produce water for folks, right? So in terms of our reactivation services for the point of entry system, these are kind of like the steps you take to take that spent material from a point of entry system and have it reactivated as a means of disposal. So the first step is this distributor is establishing a service area based on Calvin Carbon's guidance. So it's typically, you could say like a certain region or a certain state. Really will work with us on like what those boundaries would be. And then we would provide a quote for the distributor for the actual testing of the carbon material, make sure that there's nothing in that media that might, not meet our permits, et cetera, et cetera. Then the distributor is then coordinating sample collection and shipment to us for the actual testing of that medium. And then once we receive those samples, we test them, and based on the results, we either provide an approval or a denial for reactivation as a means of disposal. Now, if approved, then distributor is then working with their dealers to pool media into a central location for that service area. And then the distributor is then shipping media to Calgon Carbon for the actual reactivation services. And from a minimum quantity perspective, that will be about 30 cubic feet of media or 1,000 pounds per shipment, basically. And once we receive that media, we'll basically reactivate the spent material and then it will be reused in an industrial application, making sure that folks that are using this material know that it's not just, the PFAS being destroyed, but the media itself is being reused in a sustainable manner for a different application outside of drinking water. And that's all I had, and I think we're right on time. So thank you for your time, and I'll turn it over to Olivia for the Q&A.
Yeah, thank you, Angie. Thank you, George, for both of your presentations. If you guys have questions, please put them in the Q&A box. So while we prepare for questions, I have a few reminders. A follow-up email will be sent out with a link to the webinar recording, and we also post them on WQRF's YouTube channel. Our next and final summer school session is on August 27th, and we will be exploring PFAS treatment with granulator activated carbon. Additionally, if you are WQA certified, you can earn 0.1 CPD by attending this live. For additional 0.15 CPD, you can complete a short quiz. So look out for an email from me or the certification team for that quiz. So we can begin the Q&A. So what kind of carbon was used in your testing, and did you do any comparisons between different types of carbon?
Very good question. So I believe it's coconut shell. We haven't done the test of a wide range of materials. However, in our another study, we tested granular active carbon, carbon block filters. I believe all are made of coconut shell, and doesn't matter which manufacturers they are coming from. All the active carbon filters perform very well with more than 99% removal efficiency for PFAS removal.
Thank you, George. Angela, this one is for you. How many times can you reactivate the media?
So It depends. In theory, if the media is treating a water source that's relatively clean, because you are able to add makeup material to it, so it's like, let's just say 80% of the media that you, or 100% you're sending through the reactivation kiln, through that kiln, you could be losing 15 to 20% of that media to fines through the reactivation process. So you're adding in that loss of in terms of fines with virgin material. So you're always getting back, if you're doing it as a reusing ability, a mixture of reactivated and virgin makeup combined. So technically you could be keep going and going and going and it will just perpetuate its cycle. There are instances though where due to use, the granule is basically the physical properties are deteriorated a little bit, whereby like the effective size of the material is smaller, so the pressure drop through your system might be too high. So you'll want to do a virgin reset. But from a point of entry type of system, in those cases, because the media is going from these, I'm going to call them smaller systems being combined into one location by the distributor and then sent for reactivation, the material that then is reactivated just goes into what we call our pool that is then used to supply industrial applications. So that in itself can go on and on and on and on. So it is site specific, but there is a good chance that you'll be reactivating for over 7, maybe even 10 cycles without issue.
Awesome. Another one for you, Angela. What does the PFAS turn into when thermally destroyed?
Yep. So when you're actually mineralizing that compound, you're generating hydrofluoric acid, essentially. And that acid is then captured by our chemical scrubbers. So it's no longer PFAS, it's an acid, and then it's reduced to fluoride ultimately through that chemical scrubber.
Perfect. George, I have a question for you. It's kind of a two-part question. Does higher retention by the activated carbon filter imply that PFAS will pose less of a recontamination risk when the carbon is disposed via landfill? And does this show that landfill leachate from GAC disposal sites won't be a large source of reintroducing PFAS into the environment?
Very good questions. That's our original research question to try to understand if they may pose higher health risk. What if they release from the spam filters? Based on our study with this kind of wide range of conditions, yes, I would say they are less likely to be leached back to the leachate. Before the studies, we didn't really know. We are not sure about if that's the case. But as majority of the PFAS are retained in the filters, so I would say we can safely say only a small fraction of PFAS will end up in the leachate. Yes, we're gonna have less risks. As to the actual health risks, probably additional exposure studies need to be performed. So including the actual concentration, exposure time, and maybe competition of other chemicals. And also we have to keep in mind, whenever we're talking about the PFAS within landfill, we have tons of other solid waste. They are not designed to absorb PFAS, like carpet and all those like packaging materials from the lunchbox. All those materials may contain PFAS. So a comprehensive study to look at all the different sources and their potential risk, I think, is much needed. So we can understand better, to see how we best manage this potential health risk.
Thank you, George. Another one. What percentage of influent PFAS was retained on RO membranes, and on average, what percentage were you able to leach back off in your testing?
If we are talking about the RO membranes, we have more than 99% of removal rate. And when we talk about the PFAS coming with the materials is a trace amount. So it's relatively small. And also when we look at the performance of the RO filter, so the majority of the PFAS are rejected back into the waste stream. We call it the concentrate or R reject. So the relative fraction is relatively small. So we are not seeing a significant adsorption with additional PFAS from the drinking water.
Thank you. Angela, a question for you. On average, what percentage of the carbon is lost during the reactivation process? And then does long/short chain PFAS have any effect on that reactivation process?
So in terms of about how much, I would say somewhere between 10 to 20% is what you typically see in the sense of losses being the granule or the granule is breaks down to fines and is no longer considered a grain at that point. And in terms of short chain and long chains, our studies have looked at both and they are not impacted. They're all basically 99.99% removed.
Thank you. Another one for you. How do you assign country of origin to the reactivated end product if the pool of carbon comes from different countries?
Gotcha. So when we do reactivation, we are basically doing that for our media. So that would be something I should clarify. Um, because of the different qualities of medias, when we do this pool reactivation, it's basically typically bituminous coal based and it's domestic GAC that gets reactivated. There are facilities that do coconut reactivation, but most facilities that are looking at PFAS removal don't use coconut GACs. They're mostly using, at least at full or like larger scales, it's typically bituminous coal. So for that service, it's basically you had, for example, FilterSorb installed in your point of entry system. It's now run its course. You need a change out. That spent FilterSorb material will be pulled by the distributor, shipped to Calgon, and we would reactivate it. And since it's FilterSorb, it's all basically local to the US, and that's kind of how we manage it.
Thank you, Angela. George, I have a question for you. Can you elaborate more on the AC filters retaining PFAS in low pH conditions? One slide showed a spike in pH of 4, and what are the possible causes of this?
Sure. So we performed the testing. I realized, we had multiple peaks of the PFAS and under different pH. The most likely reason for this high variability or inconsistency was likely because in one of these bottles, under the low pH conditions, we have more of the particles with a higher amount of PFAS retained. Because if you look at the carbon block filter, water goes from the outside, and you're gonna most likely have higher amount of PFAS accumulated on the surface in the external side, and they have less amount of PFAS. When you do the grinding, you really don't know what a fraction of the PFAS end up in a specific bottle. And also we realized we have 2 peaks in the pH 8 and even higher. So that doesn't really make sense. We realized for many of these retention studies, I mean, this is an intrinsic shortcoming that we had to avoid. So that's why we grind the filter first, then we do adsorption, make sure they retain the similar amount of PFAS, then do the desorption or retention studies. Then we got much more consistent results. So I believe that is related, the kind of peaks under low pH is related with the intrinsic preparation challenge when we precise the samples. And I think we have to deal with that and solve that issue.
Thank you, George. Looks like we have one final question for Angela. Have you done any investigations of variations in PFAS destruction efficiency when using the EPA methods you mentioned versus evaluating it via something like total fluorine recovery methodology?
Yep. So we have done both, as well as we've been working with the EPA on a lot of these reactivation studies. And they've actually come out with at least one that's already fully published, OTM 50, which is looking at your greenhouse gases as well as products of incomplete combustion. So PFAS that might have started as a PFOA but didn't fully decompose or mineralize. And then they also asked us to run another method that is not yet published, but they've been working on it, that's looking at reform PFAS, called, I think it's EPA method 0010, or also sometimes referred to as OTM 55. And so what we've been doing is not just the fluorine, and the reason with the fluorine is that it's hard to do a fluorine mass balance on these systems because the starting concentration of fluorine is not high enough for the current technical or detection limits to really capture everything. So we switched over to the EPA's suggestion of doing the OTM 50 and 55 to make sure that, all right, well, can we at least prove that we're not having partially decomposed PFAS coming out, or greenhouse gases, or reformed PFAS, and the OTM 50 and 55 results from our studies are basically non-detect at our stacks. So we know that the actual PFAS compound is getting mineralized. We know that it's getting captured in that chemical scrubber. But in terms of fluoride analysis, I think the first paper is going to look into that, and that second paper is going to show the data on these new methods that the EPA is coming out with.
Thank you, Angela. So those are all of our questions for today, and we are at time. If you have additional questions, you can email us at foundation@wqrf.org. And thank you everyone for joining us today, and we'll see you when school is back in session on August 27th.
Thank you. Bye-bye.
Thank you, everyone.